Hello and welcome. In this lecture, we will learn how to write lines of codes for gradient descent in Python. In our previous lecture, we learned about the theoretical aspects of gradient descent and least squares, and where do we prefer gradient descent over least squares, and what are the advantages. Now let's quickly look at how can we build that in Python, and of course we will also see how we can reuse these codes for other problems as well, because sitting and writing lines of codes in your programming journey could be time consuming. So try and make as much as or as many reusable programs so that you can use it when it is required. Okay, first things first, let's get the required libraries for preprocessing, and then we will get the required libraries for regression, and then we will set the program. The first, if you remember, we have learned about class and objects before, user defined functions. We will use that. The objective of using the class and user defined function is that we can use this program to run different models or to solve different problems. I mean, simple linear regression, either using least squares or gradient descent. We will perform both, and we will have a quick comparison also. Okay. So first, I'm gonna define the class. Maybe a class I'm gonna define as regression. Any name you can give, and then I'm gonna define, and I'm gonna initiate init. I'm gonna provide self, and self is basically to point it towards the object what you're creating, and the variables what we require in regression is basically x and y, right? Your independent variable and your dependent variable. So we will declare that x and y here. Your job is done, and now let's go ahead and call the libraries required for it. So first one is obviously you need import pandas as pd, and then you will obviously require numpy, import numpy as mp, and then pre-processing you would require, sometimes you may require scaling activities to be done, so you can easily call them and keep it. Before that, I need some statistics, so I will import statistics and keep it. That's important for me. And then from Skippy, I will import stats as well, which is required for me to run the normality test and so on and so forth. So I will import from Skippy, import stats. I'll keep that because that is required for me. And then from a pre-processing perspective, I will require, this is ideally, the Skippy, we can have it under regression. Oh, that's okay. We can keep it here. There's no problem. And from a pre-processing perspective, you will also require to have the scalars. Not that you will use it all the time, but you can keep it ready in case if it is required, you can do it. So I will take from sklearn dot model underscore selection import. You need a min-max scalar if you want, and then from sklearn the same thing, model selection, I can copy paste here. I don't want to type it. From model selection, I will say import standard scalar. I think that is pretty much what we need. If I'm not wrong, I'm just going to check a quick check. Yeah, I think that's pretty much it is. Yes, and we will need the visualization. So I will say import matplotlib dot pyplot as plt. So that's important. Then I can also in the pre-processing, we can also have our train split and train, test, and split. So we can have that too. So from import, we will, okay, this model selection, this is from pre-processing. This is not from model selection, so pre-processing. This is again for pre-processing. And from sklearn again, from sklearn dot model underscore selection, I want to import train, test, and split. This I need for my modeling work. So in statistics, I have kept it ready, and then all I need is another function. Also, I will need import math function. We will need this to basically calculate certain things towards the end. So we will have math function also imported and ready. We will write what these are the libraries we needed. Libraries for data processing and pre-processing, or data analysis and pre-processing, I would say. Pre-processing. Okay. And now let's get some libraries which are required for us to run regression. From sklearn dot linear model import stochastic gradient descent regressor, and then we can also have our from sklearn dot linear model import linear regression. So those are the two things we will need for our libraries required for regression. So I will just keep that as same, give some sort of a comment so that it is easier. Libraries for the regression. And then we will also need, certainly for calculating the R square and MSE, we will say from sklearn dot metrics, I will need these two things with nothing but mean squared error, and then obviously I will need your R square as well for R2 score. So from sklearn dot metrics, I will have this import. So that is pretty much what I need for my regression as well. So I'm fine with this. Now we will start off with what is required to be done first. When you get the data set, you have your X and Y's ready, and then you have to first check whether there are any missing values. That's what we have been doing, isn't it? So we will create that, checking and treating for missing values. So what we have to essentially do here is figure out a name what you will be keeping for your data set and keep it as a standard name. So either you can keep it as data or data1. It doesn't matter. You have to stay consistent and you have to keep that name. So I will probably use data1 as the name which I will be providing while I'm calling this function, especially for the X and Y. When I'm calling the function, I will use data1 as the base sheet name or the data frame name. So I will just use that. And the first one is for a for loop I will use, and I say that for say I in data1 find out dot is null dot sum. You remember, if you use this command, it's going to provide you the number of null values. Okay, so for I in that, I'm going to iterate and ask if condition is I is greater than 0, then what I want to do is I want to replace data1 dot replace your null value np dot nan with what? I want to use a strategy or a method. If you remember, method is equal to, say, let's use forward fill, f fill, and then I want that to be replaced directly into the data sheet itself. So I'll give in place is equal to true. Okay, so I've asked them to replace it. Else, if there is a situation where the I is not greater than, then I will say print there are no missing values, isn't it? So I'm clear with that. So my checking of and treating of missing values has been taken care. Now I can proceed. What is the next step I generally do is to ensure that there is a linear relationship. So there is a spelling error here, so just to ensure. So the next thing what I'm going to do is, let's do step by step. The preconditions need to be validated. That means you're going to validate whether there is a linear relationship, isn't it? So first one is visual. So I will plot plt dot a scatter plot I want between x and y. And then I will say plt dot show. It is for me to see the graph. Okay, and then what I will do is a scatter plot is absolutely fine to see visually where it stands in terms of a linear relationship. And now it is very important for me to understand the correlation also. So what I will do is I will use the np function here. So I will say that if my np dot correlation coefficient, if my np dot correlation coefficient of my x and y is greater than, say in reality you may not get correlation coefficient as 0.9 or 0.95 always, because it's very difficult to get that. That's an ideal world. So you have to make some sort of a compromise. So maybe for the model's sake, you can put it as 0.65, or it's a positive relationship, isn't it? So if it is a negative relationship, we'll just copy this, and then we will say that np.coef is less than, say, minus 0.65. That is when you will say that there is a negative correlation, since it should be a negative correlation coefficient. If this is the situation, okay, I'll close this, then I would say, if this is the situation, I can continue with my next step of regression. If this is not met, I will not want to execute anything. I will want to simply stop my analysis and give the result as it is not possible. So we don't really need to write it now. We can write it at the end. Please keep in mind that you have opened an if loop and you are basically fitting all your programs within this particular if loop. Only if this particular condition is met, you will go ahead straight away to perform regression. Okay, so your missing value is done, and your now correlation coefficient has been done as well. Now if this is done, what I need is basically to fix my x train, x test, y train, y test. Please be careful because you have to ensure that it's all having the right and consistent spellings, which is important. So you have x train, x test, y train, and y test. And now which library you're going to use? You're going to use train test split. So you're going to use train test split and then copy and that, and then say that my x and y variable and test size I am putting say as 0.3% or 30% test size, and then I would say random state as for now let's keep it as 0. So your x train, x test, y train, y test, and all of these things have been sorted now. Now imagine, remember one thing, for you to have your SDG, this is an array with just one dimension. So we need two dimensions for x and y test, correct? So we will go ahead and create those x train, x test, and y test. We have to reshape it. So we will we don't need y train at this point in time. So we'll say x train is equal to x train dot reshape -1 to 1, so that it will make a two-dimensional one. And y train I don't need it at this point in time, but I need x test. So I'm doing x test is equal to x test dot reshape -1 and 1. And I'll need my y test data as well. Y test is equal to y test dot reshape -1 and 1. Okay, so I have got these things in order. So I have my basic checking of three conditions done. Three conditions have been checked now, and now I'm going to set up my variables, which I've done here. So I'm just writing it down to ensure that we do not setting up variables have been done. Okay, now what do I need? Now what I need is very, very important, that I'm going to start with my regression, isn't it? So I'm going to start with my regression. So getting ready for regression, isn't it? For regression, you can do it patiently, because if you make mistakes you will spend more time in troubleshooting. So the first thing what I'm going to get is maybe I will make it as SLR, simple linear model, is what I'm trying to say. So I will use which regressor? This one, SDG. So getting ready for regression, so I'll say it is SDG with SDG, Stochastic Gradient Descent, SGD. So SLR, I'm going to use this regressor, and I will say that dot fit that for x train and y train, isn't it? So this is the fit which I'm asking. Dot fit is done. Now the next one what I will ask is y predict. Get me y predict. So I'll put that as y predict is equal to, say, SLR dot predict, and what I need to use, x test. Using this, please predict it for me. Okay, and now that prediction is also done, the next thing what you need is the r square value. The r square value you need. So r square value of what? So y pred is already done, and you have y test already completed. So r square, I'm going to use this particular r2 square, r2 score here. So I'm going to use that. And R2 score of what? I want to use my Y test and my predicted Y value, Y pred, isn't it? I'm going to use that. And now I also need my mean squared error, isn't it? I need my mean squared error. So I'm going to use mean squared error. So I'll call it as MSC. MSC is equal to, say, mean squared error of what? Again, the same thing, Y test and Y pred. And Y pred, isn't it? Okay. And now I want to print my results for this, right? What print the R squared value for SDG is R squared. Put a comma and this variable R squared. Get an R squared, isn't it? And now the next one, I want to print my MSC also, so I'll just use this command here. I want to type so many times. So the MSC value, I will make it MSE value, mean sum squared error value for SDG is MSC. Okay, perfect. That completes your SDG regression codes. This is the crux of it, right? If you have to perform the regression, this is what you need, and that is something what you have already written. And now it is important that once this is done, I need to perform some post validation, post model validation, right? So we call it as post model has been built now, post model validation. First, post model validation, if you remember, what is it? It's basically you need to ensure that the residuals of it is following a normal distribution, or residuals are random in nature. So randomness is always checked by whether the residuals follow a normal distribution. Okay, so first let's calculate the residual. I'll call it as residual only. So what is residual? Residual is nothing but the difference between my Y test minus my Y pred. This is what my residual is, right? If I have to take a difference of my Y test, which is my original Y value, and the predicted value, what is remaining is the residual. And mind one thing, that if you have to be very sure that the residual what you get here is actually a one-dimensional array, isn't it? So I definitely need it to be a two-dimensional array. So I'll say that res dot reshape -1 and 1. So this will make it to a two-dimensional array. Now for this, first thing what I will ask is to plot a histogram for me. Plot histogram of residual. So I will have a visual understanding of what the shape would be, and I will say plt.show, so that you please show me the histogram. So that's done, isn't it? And now if you remember, we need to do our normality test here. So I will use Shapiro. So we can name anything. Sharp norm normality test norm, we will name it. So Shapiro, I'm using Shapiro. But where do I use Shapiro from? I'll use it from stats. So stats, if you remember, we had downloaded and kept here stats. This is where we need stats. So stats been done. Okay. So stats.Shapiro, and of what? I need to check the normality of residuals. That's what my residual value. And then I will ask, okay, print this particular variable for me. Okay, print this. And then if you always remember when the Shapiro test was done, there was first the test statistics and second was the p-value, and that was in an array. So if the p-value is greater than 0.05 was when we will say that it is a normal distribution. So you can always print it like this, print, and say that the p-value, before printing we have to give an if condition here, isn't it? Because if your sharp norm this particular thing is an array and the second value of it, so that is 1, array of 1, we are accessing that value. If SHEPRO1 top norm 1 is greater than 0.05, okay, then you print that, you print and say that the residuals follow normal distribution and we can accept the model. If otherwise, if else, we would say print residuals do not follow a normal distribution and we cannot accept the model. These are the two conditions. So we're very clear on what we are printing here, isn't it? So we printed that. The next one is the mean of the condition. If you remember, the mean of the residuals must contain the value 0, which is very, very important. So first is identifying what is the mean of the residual, and also we need to identify the confidence interval of that mean. The mean ranges from where to where, and 0 must be within that range. If it is not containing 0, that means your residuals does not have a mean which contains 0 and which cannot be used. So that's one more condition what we need to check, and we're going to check that. Okay, so we have done that, and first thing is I want to know what is the mean of the residual. So I'll probably call it as mean residual is equal to, this is where I will use statistics. Statistics dot mean of residual. So this is the library what we have kept ready, statistics, isn't it? Didn't we use statistics? Yeah, statistics. That's the library we'll use. The mean residual is done. Okay, and then now I want to calculate what is the upper confidence interval. So upper confidence interval is basically calculated using a formula. I'll just write that formula for you. It's easier to remember. So the formula for calculating the confidence interval is basically x bar, which is your mean, x bar, or your mean I would write, plus or minus, okay, z alpha by 2, c alpha by 2, which is the z value when your confidence level is at 95%, is what we are substituting it. Most of the calculations we need a confidence level of 95%. So corresponding value of z alpha by 2 at 95% confidence interval has to be found out, and then it gets multiplied to the standard deviation divided by square root of the number of samples. Okay, so this is what basically which will give you mean, this mean plus a particular level and minus a particular, so that becomes the range, and you need to ensure that 0 is contained within that range. Okay, so upper confidence level, what I'm going to use here is mean res. I've already got it because that is what I need, and I will type it here, plus I want to add, and then what is z alpha by 2? Always remember that z alpha by 2, I'm going to type that here so that you also have a fair understanding of it. Z alpha by 2 for value of Z alpha by 2 for 95% confidence level is 1.96. This is a standard value. Okay, 1.96. So I'm using that value 1.96 here instead of Z alpha value, and then multiplied by what? Multiplied by, the entire thing gets multiplied by, first is the standard deviation. So which library should I use for standard deviation? I can use statistics again. Statistics dot stdev, standard deviation of what? I want to get the standard deviations of residuals, which is done. Okay, and then again I want to get the square root out of this. So where I square root I can easily calculate by using this particular library, math, math. So I'll just use math.sqrt, square root of what? I want to know the number of samples we are using. The number of samples what we are using to calculate residual is from nothing but your y-test and y-pred, isn't it? So you can go ahead and say that this is the length. It is the length of your, say, y-test. This is all what you need. So the length of the y-test will make sure that you get what you want, isn't it? That's pretty much it is. But now you just need to take care of your brackets, which is really important here. So I will I've used these brackets here, math on square root, this is done, length, this is done, and this is done. So if you want an additional full cover bracket, you can provide this bracket, which will take care of your entire requirements of brackets, and that's basically upper confidence interval. And then you need certainly the lower confidence interval as well. So I'll just put it here low and change it to lower confidence interval, and all I need to do here, lower confidence interval, and all I need to do is here just make it to minus. Okay, so you have your upper confidence level and your lower confidence level here. And then what is the next condition? The next condition is obviously I need to check whether 0 is contained in this or not. So I can always use an if condition. If, I'm going to ask that question, if, okay, if upper confidence level, okay, is greater than 0, and I need and, or and, yes, I need and lower confidence interval, and lower confidence interval is should be lesser than 0. Only then, because it's a negative and a positive value. So negative, you have a negative and positive value, obviously your 0 will be contained there, right? So if it is basically to ensure that you have a negative value and a positive value as these two things, and then it is taken care. So if upper confidence level is greater than 0 and lower confidence level is lesser than 0, if this condition is met, then I would say print 0 is contained, since mean of residuals contain 0, we can accept the model. Okay, since the mean of residuals, maybe the mean of residuals interval contains 0, we can accept the model. And if it is not, then else you can say that print, since I'll use the same thing, I don't want to print it again and make changes there. Since mean of residual intervals does not contain 0, we cannot accept the model. Okay, so this is the condition what we are also checking, post model condition, that if this is true is when I will have to use the model, and if it is not true, I will not be able to use the model. So that is pretty much it, where we are talking about the post model condition checking also, and similar things you will have to work out for your least squared method also. So all I need to do is basically copy the entire code here, because I want to run this for my least square also. So I'll go down here, and then I will copy that, the entire thing here. I'll copy this, so you'll have to do a little bit of alignment changing. I'll copy this. So you see that it's getting copied here. So SLR, the regressor changes, it will become linear regression, because that is linear regression. And this you can that's the only change, because this code you have copied basically to getting ready for regression least square method, because this method in above you've used the SGD method. Now you're using least square method, and the only change here is basically I need to use the linear regression, this particular library for that linear regression. So I'm just using this. You can even copy paste this, I just wrote it there. So you can come back here and then just copy paste here as well. So that's also done. Okay, so you can do that. So that is basically taken care, and this is post model validation. All you need the residuals from, you can say, least square. You can say that, isn't it? Least square from least square, and here the residuals from, you can say, SGD, residuals from SGD, you can call it stochastic gradient descent. So wherever the residuals, wherever you're doing it for SGD, you can mention the residuals from SGD. You can call residuals from SGD. It's all to basically differentiate your answer from least square. You can put it from least square. Okay, so that is pretty much done, and your least square method is also done. Okay, and then if you want to, you can do one more thing here. You can print. You can provide the print command here. Say print. So you can the upper confidence interval for, say, this is least square. So you say that this is, say, percentage. I want to reserve it as 3 decimal point float. Okay, this is what I want to the upper confidence interval for least square is. And then what is the value you want to provide? You can just put it as percentage upper confidence interval, isn't it? Upper confidence. You can provide it here. That's all what you need. And you can also print the lower confidence interval. So I just need to provide this code, copy and paste here the lower confidence, and that is also printed. So your mean of residuals, if that is not printed, you can even print that here. So print we will use the statement the mean of residuals from least squared is, again you can preserve it as 0.3 f, it's a float variable, and then I'll say put percentage, and I would use here, this is what I'm preserving here. Isn't it? I just reserved that bit for us. Okay, so that is also done. And here, if you want to do it the same way, you can copy and paste this command here. These are all reusable codes, isn't it? So we have calculated the mean res here, so you can come down, copy paste here. You can say that instead of least squares, you'll say that SGD. This is SGD, isn't it? And then here you can copy the entire these two things, and least square, instead of least square, you can go ahead and put it here, copy and paste it, just to ensure that the intents are right, and you say that is SGD. Type it for me. SGD. So you have almost completed your program. It is with the way we have constructed is that this is defined as a regression class, and this program you can easily copy paste and provide different data set and get the results what you need, isn't it? So I will execute this and see shift and enter. For the first time we're executing it. Let's see if there is an error. There are no intent errors as of now, but we forgot one thing, the most important thing, because although I reminded you to remember that we have started here with an if condition, isn't it? This if condition, if correlation coefficient is greater than 0.65, and what if it is not, else what I want to do, I want to basically stop my regression, because if the correlation coefficient is not even greater than 0.65 or less than -65, I do not want to continue. So I will close it by writing an else statement here. That else statement will come here. So it should be out of this, and this should be the if statement. It should be aligned to this. Okay, so else, I'll give that else statement here, print correlation between x and y is very weak or no correlation, since correlation between x and y is weak, very weak, we cannot proceed with regression. Okay, so that is important, because you have to close this, isn't it? We have opened an if statement here. So we have to come down and close it. If this condition is valid, is when the entire execution happens. Otherwise, it directly comes to else and it gets stopped. Okay, so I will shift enter. This is done. So now what have we used here? It is data, isn't it? Data 1. Data 1 is what you have used here to start off with. So I will name my data set. So I will call data 1 is equal to pd.read. You'll use the same data set, if you remember, that was salary data .csv. This is what I want to use. And then now I'm going to PD is not there, because PD we have done only within the defined function as a local library. So we will also need to write it once here, import pandas as PD. Okay, so then this will be taken care. Just to quickly check whether I've got the data right, salary underscore data dot csvpd dot read underscore csv. Okay, so data1 dot head. Just want to ensure that I got the same thing. Okay, now what I want to do is I want to call this particular function, this class, and what I will do is this class I need to provide two variables, the x and y, isn't it? This x and y I need to give. All I need to go ahead and do is I will use data r1 dot, what is the x for me? Years of experience. So I copy this years of experience and I put it here, and then I want it as an array, so values. Okay, and then what is my y? My y is salary, so data1, I'm just calling data1 here, and dot what? Salary. I can copy paste or I can type, but ensure that you type in the same uppercase, lowercase, and all of those things should be exactly the same. So then dot values. Again, I've converted this into array, and I called regression. So if you want to see what is regression, you just type to regression here, and then just type it is it's a class, which is the main class. Okay, so that regression I'm using here, and I'm providing the values of x and y, and shift enter, and let's see how the program is working. Okay, so we have some errors. So not matplotlib. Okay, so here there is no, so there is a spelling error we created. So this is a process, matplot. Okay, so this we have tried to solve now. So shift and enter, shift and enter, shift and enter, shift and enter, and shift and enter. Let's run the program. So this is an iterative process, guys. So if you have got errors, the truth value of array is more than one element is ambiguous. So dot all. So where is the error? So the error is np dot core coefficient dot values dot values. This is fine. This is fine. So here is the error, np dot x and y. So let's go back to that and check what is the error. So could you figure out what is the error? The error, I think here. See, if you remember when we did correlation coefficient, it came as a two-dimensional array with 2 rows and 2 columns where it showed the correlation between the same variable and the different variables. So it's a 2 columns and 2 row matrix. So what we are interested is in only one particular value, because that value has to be compared, right? So I do not want the correlation between x and x. I just want the correlation between x and y. So the matrix, if you remember, it first will give x and x, then x and y, then it gives y and x, and y and y. So that was the correlation matrix. So I just need the correlation matrix for the first row, and then in the first row I want the second value. So I will put this, and the same case here as well. I want it for the first row and for the first value in the first row. So correlation coefficient, this is what we have done. So correlation coefficient, if you look back into your lectures, you will find that it comes as a 2 by 2 matrix, 2 rows and 2 columns, and we just need the top right value. Top right value can be accessed using this. So shift and enter, shift and enter, shift and enter, shift and enter, and let's see what is what is the next error. So the function object is not subscriptable. Here it is 0 and 0 coefficient. Oh, okay, here again a mistake. See, you're not paying attention. You have to pay attention, otherwise everything goes. This has to be after x and y, because that is what I want to do, and then after x and y I'll put this. Shift and enter, shift and enter, shift. So this is called as troubleshooting, guys. This is how we troubleshoot and get to our values. Can't convert an ND array to numerator. So the problem here is in which row? Statistics mean dot. So this is basically an ND array. Numerator and denominator is not possible. So error comes in this particular mean res. So mean res, yes, here. Mean res is here. So I need to get it into a reshape, that is dot reshape, I want to make it to a single dimension. Here I made it to a single dimension here, and I will make this also to a single dimension, where I'm calculating as dot reshape as -1. I want to only have it in the form of a row. Okay, so in a particular row, that is what I want, and I've just done that, and that is the error. Convert into a numerator and denominator has to be converted. Okay, so I just need that as particular row, and that is what I have asked here, because I cannot calculate when it is a two-dimensional array. So I've just made it to a one-dimensional, just one row for here and here, and shift enter, shift enter, shift enter, shift enter, and let's see what is the next error. Name statistics is not defined. Statistics, see, there is a spelling error. Which one is? Yes, see, this is always what I would suggest. Just copy paste from the library so that you don't commit a mistake, and then you will not spend time in troubleshooting this. But this is how the real programs, whenever you write programs, it'll keep throwing errors. You'll have to troubleshoot it, and I'm not sure whether we have done the same mistake here as well. Yes, statistics, troubleshooting. Okay, shift enter, shift enter, shift enter. What's the next error? Can't convert NP array. I think we may have left it somewhere here. See, here again, I want to calculate the standard deviation. So I will have to have from a two-dimensional array, again, I will have to give it as one row. So I'll reshape it and say that it is -1. Okay, the same thing I will do here as well, because the reshaping is, because this residual we have already converted, if you remember, -1 to 1, so that becomes a two-dimensional array. So I do not want two-dimensional array, I just want a single dimensional array, just one row, so that all these statistics can be calculated. So I will have to change it here as well. So I will change it as reshape -1. These are all small things, but it matters. Reshape -1. Okay, I hope that will take care of that error. Let's see. Okay, so our program is working now. Let's look at what is the result. Our results, we have to look at our results now. Where is the SDG result, the R square values, and the R square values here? The mean residual value, this is the R square value for SGD, and the upper confidence and the residuals appear. So I don't think we have asked for the R square value here. Print the R square value of SDG. This is least squared. Okay, this is least squared, and this is SDG, least squared. So that is why we are getting confused. The least square. Okay. So this is SDG R squared value 97.46 and 97.40. Okay, see guys, so this is a very small data set. It has only very few values, so but still there is a slight increase in the R square value of your stochastic gradient descent. It's not SDG, it's SGD. So let's change that. It is SGD, 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 SGD. Yes, I want this to be SGD, SGD, stochastic gradient descent. So stochastic gradient descent is giving you these values. So this is SDG value. We'll run it again to ensure that Get it right. The 97.40 is least squared, and 96.75, I'll run it again because it's random. 97.54, 97.40. You see that there is a slight increase in your SGD value when you run it multiple times. It's a 97.40. So SGD is capable of giving slightly better, and your MSE value also 221.552 here, it's 233. So the value of error is larger in your least squared method, whereas this is lower in SGD method. Okay, one more thing what you really need to look at for is the mean residual value, and you have the first graph, which is the linear graph, which is absolutely fine, and then you are doing your Shapiro test. The residuals from SGG follow normal distribution, and we can accept the model, and mean of the residuals is minus 16659. And here the upper confidence and the lower confidence, see here there is a mistake because it is printing both the same values. So for SGD, look at the program. SGD, patients are, see, you have put upper confidence interval in both the places. You need the lower confidence interval, don't you? Yes, so lower confidence, what you want to type for you. And similarly here, it's also the lower confidence. While copy pasting, ensure that you have the right values, because otherwise you will have issues like this. But that's okay, you can always correct it, and that's what we are trying to do here as well. That is okay. So here you see that the lower confidence value is 27, and the upper confidence is the lower confidence is minus, so this minus and minus, so this definitely has, since mean of residuals from SDG interval contains 0. The 0 is in between these two values, right? That's the holy. So if it is two positive values or two negative values, you will not have 0. So it's one positive value and one negative value. So 0 is contained, so you can accept the model. Okay, so that is basically what you have to check for both the models. I'll keep running this, so you see that the values keep changing. So 97.5 and 97.40. So this model is capable of giving you more values, and same thing for SGD. You have found that this is also true, where 0 is in between, and for least square is also, it is true, it is 25 and minus 28. So 0 is definitely in there. So both the models are valid, and SGD is slightly better than the other one because your R square value is 97.5 here. When you run it, you see that the values keep changing because it's random state. So you see that the value is 97.4 for least square. So there is a slight improvement in SGD, stochastic gradient descent, and that is the reason why we say that stochastic gradient descent is capable of sometimes giving you better results. But you can always run this and check this. And you can, the benefit of writing this particular program is you can use this program for pretty much all the data sets whenever you want to run simple linear regression. So you can use either SGD or least square results, compare it and use it whenever it's required. So this is where we have used a lot of things what we have learned so far to write a program. This is how generally you write a program, and then how to troubleshoot. And I will provide you another data set. Please do try to construct this so in such a way when you write programs, write in a smarter way so that you can reuse it. Now next, if you want to use this program, you just need to copy paste this and then run it elsewhere, isn't it? So okay, so I hope that you understood how to execute SGD and least squares, and what is the post condition and preconditions, how do you validate it, and finally take a call. Okay. And I shall see you in the next lecture. Bye for now.